Hello everyone, I'm Soo-young Choi, and today I'll be discussing the topic of spin transistors. The concept of using spin for computational purposes has roots in the discovery of electron spin in 1925. The rise of spintronics began in the 1980s with the discovery of giant magnetoresistance, in short, GMR, by Albert Fert and Peter Grunberg, for which they won the Nobel Prize in Physics in 2007. GMR technology, which led to the development of highly efficient read heads in hard drives, showcased the practical potential of spin-based devices. This set the stage for the exploration of spin transistors in 1990s. In 1990, Data and Des proposed the first conceptual spin transistor, often referred to as the Data-Des spin transistor. They envisioned using a semiconductor where electron spins could be manipulated via electric fields. First, I'm going to explain GMR, which set the stage for spin transistor. The GMR refers to the phenomenon in which the electrical resistivity of a magnetic material changes greatly in the presence of an external magnetic field compared to when the field is absent. This phenomenon is followed by quantum mechanical effects, which is spin-dependent scattering, that results from a layered magnetic thin film structure, which has several nanometers thick. This structure is formed by alternately laminating thin layers of ferromagnetic material and non-ferromagnetic material. For your information, ferromagnetic material is one that exhibits a strong form of magnetism due to the alignment of the magnetic moments of its atoms. In the figure 1, we can see two different ferromagnetic materials sandwiched by a thin conductor layer. Ferromagnets can retain their magnetization even after an external magnetic field is removed. This property, called remanence, is why materials like iron, nickel, and cobalt can become permanent magnets. Each ferromagnetic material has a specific temperature known as the Curie temperature. Above this temperature, the thermal energy disrupts the alignment of magnetic moments, causing the material to lose its ferromagnetic properties and become paramagnetic. But this Curie temperature is much higher than room temperature, which makes ferromagnetic material more practical. As we can see in figure 2, according to the microscopic mechanism of conduction, the electrons in the metals do not travel straight along the electric field when conducting electricity, but continuously collide with the atoms in the lattice position, which is called spin-dependent scattering. And the electrons change the direction of motion after each scattering, as you can see as in the blue line. The average distance of the electrons moving between the two scattering is called the mean free path. The smaller the probability of electron scattering is, the longer the mean free path is, and the lower resistivity is. After the spin diffusion length, the spin flips. For example, an electron that begins in spin up state will eventually end up in the spin down state. However, since the spin diffusion length is usually much longer than the mean free path, we don't have to worry about changes in spin state in a GMR structure. Based on the paper by Bybek and Mario in 1988, when the magnetic moment of the ferromagnetic layer is antiparallel to the electron spin, electrons are scattered with high probability and are reflected back. Therefore, with no external magnetic field, spin-dependent scattering is strongest and the resistance of the material is highest. However, when we apply an external magnetic field and align the magnetic moments of the layers in the same direction, electrons can pass through the layer B with much less scattering than in the previous case. The spin-dependent scattering decreases and the material resistance stabilizes at a minimum level, as you can see in figure 5. Now, I'll explain data and DAS spin transistor based on GMR structure in figure 9. Both spin polarizer and analyzer are ferromagnetic contacts, and a spin polarizer injects electrons with a specific spin orientation into the semiconductor channel. A spin analyzer is for detecting a spin-specific orientation. Unlike GMR structure, narrow bandgap semiconductor is located in between ferromagnetic materials for data and DAS model instead of conductive materials in figure 9. The reason why they used narrow bandgap semiconductors is indium gallium arsenide is that they provide strong spin orbit coupling for controllable spin precession and offer high electron mobility to preserve spin coherence over longer distance. Also, narrow bandgap semiconductors allow conductivity control via gate voltage, enabling on and off switching. Finally, they are compatible with heterostructure engineering, enhancing the device's spin manipulation capabilities. Next, I'm going to explain the operational process of spin transistor based on data and DAS model, which we can see on the right. First, spin injection. A ferromagnetic contact called a spin polarizer injects electrons with a specific spin orientation into the semiconductor channel. Due to the nature of ferromagnetic materials, the contact injects electrons with spins aligned to a specific direction, creating a polarized electron current. Secondly, for spin manipulation. In the channel, which is typically made of a narrow bandgap semiconductor, spin precession occurs due to spin orbit coupling. The Rashba effect, a type of spin orbit interaction, is induced by an electric field at the heterojunction interface, which splits the energy of electrons based on spin orientation. As electrons travel through the semiconductor channel, the spin precess, meaning the spin direction, rotates at a rate determined by the strength of spin orbit coupling and the applied gate voltage. To help your understanding about spin precession, I attached a video that explains how the spin precesses when AC magnetic field applied, which has direction from east to west. I'll keep going with the gate voltage explanation. A gate voltage applied to the channel modulates the strength of the Rashba spin orbit coupling, which in turn affects the rate of spin precession. When the spin of the electron aligns with the direction of the spin analyzer at the output, the device exhibits low resistance. When they are misaligned, the resistance increases. Finally, at the stage of spin detection, only electrons with spins matching with the analyzer's orientation pass through with the minimal scattering, resulting in low resistance. If the spins are misaligned with the analyzer, electrons face higher scattering, resulting in high resistance. A spin transistor operates similarly to a conventional FET, but manipulates electron spins rather than charge. Regarding to the data storage and processing, this allows for a non-volatile functionality, meaning information can be retained even when power is off, potentially leading to more energy-efficient memory storage solutions. Also, spin transistor can switch states with significantly less energy consumption than traditional transistors. Thirdly, thanks to the rapid reorientation of spins, spin transistor can achieve enhanced speed for logic operations. Finally, spin-based logic could introduce functionalities that aren't visible in conventional electronics, such as certain types of quantum logic that takes advantage of entanglement and coherence. Spin transistors are a promising advancement in the field of spintronics, a domain that leverages the electron's intrinsic spin property alongside its charge. Traditional electrons rely solely on charge manipulation, which leads to significant energy dissipation. The motivation behind developing spin transistors lies in achieving low power, high-speed computing by harnessing spin as an additional degree of freedom. Regarding the topic of reducing energy consumption, a question arises from me. Is the kilogauss unit in here is large or small for a magnetic field? I believe kilogauss is quite a large unit for measuring magnetic fields. To illustrate, let's approximate the energy needed to generate 0 kilogauss to 30 kilogauss in the field over a small volume, say 1 cubic centimeter. We would need approximately 3.6 joules of energy to drive this field. Since I didn't quite get an exact answer for my question, if anyone knows, just let me know. To wrap up this slide, the potential impact spans across fields such as data storage, telecommunications, and artificial intelligence, as well as any applications needing efficient data processing within minimal energy losses. There are several competing technologies like CMOS, tunnel FETs, and quantum dots. I think everyone would know that CMOS devices are facing scaling limits due to quantum tunneling effects and heat dissipation issues at smaller scale. But spin transistors manipulate electron spins, whereas CMOS primarily manipulates electron charges. We could leverage these issues by delving into the field of tunneling magnetoresistance, which is TMR, and GMR. While tunnel FETs offer low power consumption, they lack the unique functionalities provided by spintronics devices such as non-volatility and compatibility with quantum information processing. Unlike quantum dots and qubits, which are highly sensitive to temperature and require cryogenic temperatures to maintain the coherence, spin transistors operate at room temperature and can potentially be integrated into existing technologies more easily. Still, we have several challenges such as spin injection efficiency and spin coherence and decoherence and device scalability and integration. Recent developments are focusing on materials like topological insulators and 2D materials, which exhibit better spin-orbit coupling properties and longer spin coherence times. Research in spin-orbit torque and voltage-controlled magnetic anisotropy is also driving advancements, potentially allowing for more energy-efficient switching mechanisms. As we continue to push the boundaries in this research area, spin transistors may well become a critical component in the next generation of faster, more efficient, and energy-saving devices. Thank you for your attention, and I'm happy to take any questions via mail.